So, hi everyone. My name is Ismail Bennani, and I work on the debugger team at Apple. Today, I would like to tell you about the current effort to simplify, consolidate, and document LLDB various scripting functionalities. So, if you're here, you're probably familiar with LLVM. And as described on the website, LLVM is a collection of modular and reusable compiler and toolchain technologies. It is composed of many projects like LLDB, Clang, MLIR, and so on. If we take a closer look at LLDB, we can see that it's also designed as a collection of debugging library where each component serves a specific purpose. LLDB modular architecture is designed for flexibility and extensibility. It includes, as its component, a symbol parsing library, language runtimes for expression evaluation, debugger core library, a command interpreter, and a scripting interface. And they all seamlessly integrate together to provide efficient debugging workflows. In order to interact with these components and leverage LLDB debugging capabilities, LLDB also exposes its own public C++ API to provide an efficient, robust, and stable interface for third-party clients. Thanks to this architecture, LLDB can be used in various ways, making it a very flexible tool. First, you can use it directly using the interactive command line interpreter. Then you also find LLDB in various IDEs, such as Xcode. And finally, you can interact with LLDB through Python scripting. And although both the command line driver and IDE can just link against the C++ library and call its API directly, in order to access the API from Python, you need to use bindings. And these bindings get generated from the exposed C++ API library and shipped into a Python module that can be imported by the user in their Python script to access LLDB function and classes. So as you can tell, Python scripting is a key feature of LLDB, tightly integrated into its modular architecture. On one side, LLDB exposes a comprehensive API that grants access to a wide range of debugger functionalities. This API allows you to interact with breakpoints, inspect variables, manipulate the memory, control the program execution, and more, all programmatically done through Python scripts. To start scripting with LLDB, you can use the script command, which starts the embedded Python interpreter. This allows for a seamless integration of scripting into your debugging session. And here's a quick example where in less than 10 lines of code, you can load a binary into LLDB. Then you can set a breakpoint, min.c line 42, for instance, and then you'll be able to launch your process. From there, you can get your stopped threads and with the current stack frame, and that will give you access to your local variables. And this is just a simple example, but I'll let you imagine what you can achieve by interacting with the debugger through scripting. LLDB also supports various types of scripting extensions that the developer can create and integrate seamlessly into their debugging workflow to extend and enhance LLDB capabilities. Here are some examples of scripting extensions that you might be already familiar with. You have script processes, data formatters, custom commands, and the list goes on. As you can see, it can be hard to keep track of all of them. Let's take an example at a data formatter class that will provide the first member of a type. So as you can see, this extension it needs to implement various methods with specific argument types and return types. If we look at getChild@index, for instance, here we'll do some sanity checks and use the LLDB API to get the first child member of a class. So every time you want to write a new data formatter, you need to remember all of this boilerplate code. And this also true for every available scripting extension. The user will need to write different boilerplate code that takes different parameters, and in order to use them, they also need to use different commands. And all those differences create frictions that makes it hard for developers to implement new scripting extensions. So here are the issues we're trying to address here. First, we'd like to improve discoverability. Many LLDB users are not even aware of these scripting extensions, although they could greatly improve their debugging experience. Then, we'd like to keep the documentation for those scripting extensions up to date. As you may know, it can be challenging to keep documentation up to date on such a big project with so many contributors. But it's very important to have a single source of truth. Then, we want to make it easier for developer to write new extensions and reduce the amount of required boilerplate code to keep it to a minimum. And finally, on the maintainer side, we'd also like to reduce the high maintenance costs in LLDB of those extensions, because over time, by adding new extension, we introduced some code duplication and cargo-culted some, let's say, bad practices. So yeah, let's see how we can improve all of that. So about 2 years ago, I started working on this feature called Scripted Process. For those who haven't seen my previous talk at the dev meeting of 2022, a scripted process allows you to mock a process state by making various calls to a Python script. One of the first problems that I tried to solve while designing scripted processes is that I wanted them to be extremely simple to write by our customers. To achieve that, I took advantage of Python object-oriented programming and shipped a base class implementation of a scripted process in the LLDB Python module next to the LLDB Python bindings. The base class would also have all the methods that the scripted process needs to implement. Some of them would have a base implementation so that the user wouldn't need to override it themselves, but other methods will be marked as abstract, which would trigger a runtime error if the user forgot to implement them or didn't implement them properly, like they put the wrong argument, or for instance. This base class also serves another purpose, to be the only source of truth for our extension. To do so, we make sure that every method of the base class is well documented, so we can generate a documentation page for the LLDB website from it. Speaking of the LLDB website, last summer, there was an effort to modernize the LLDB website to be able to view it on more devices, including mobiles, and provide a better experience for our user to search for existing APIs. Here, for instance, you can see the SB line entry class with a thorough description and examples, as well as all the attributes and methods it implements on the side gutter. And very soon, on top of LLDB SB API types, we also provide documentation for all the scripting extensions. So this is the one for scripted processes. This page will be generated from the base class implementation and should help us keep the website in sync with the implementation, making it the only source of truth. So let's get back to our scripted process Python implementation. Thanks to this new approach and the updated documentation, it becomes very easy for a developer to write their own scripted process implementation. They just have to create a new class, derive it from the base class that we shipped in the LLDB Python module, and implement the methods that are marked abstract. So now that we've seen how things are implemented on the Python side, let's see how LLDB calls into it from C++. So when I started developing scripted processes, took a look at how other scripting extensions were already implemented in LLDB. And I found out that over the years, every time we added a new extension, we copied some old code and made some slight variations to it. And there was basically no unified infrastructures. And that would make things very error prone, because we could fix a bug somewhere, and hit the same issue later on a totally different part of the code base. So to avoid reproducing this pattern with scripted processes, we built a new infrastructure to be able to call methods from in script files from C++, and we called it Scripted Interface. For each scripted extension, we would create a base class, a base scripted interface class that defines all the methods that our extension implements. So in the case of scripted process, you have attach, launch, resume, get thread info, etc. And scripted interface have been thought from the ground up to be extensible. And since LLDB supports various scripting languages like Python and Lua, we need different interface for each of them. Thanks to this architecture, if we wanted to make an interface for talking to a Swift file, that would require a small amount of work. Something to keep in mind is that you get one scripted interface per extension per scripting language. So let's say you wanted to add a new interface for scripted threads. You need to implement one for Python and one for Lua. And this can get overwhelming quite rapidly. However, since each scripting language have a different way of instantiating an object, a script object, and call a method, we can hoist that logic into a language-specific interface that can be shared across all extensions. And thanks to this new architecture, we have now a more robust and organized infrastructure to interface with script files in LLDB, which should help us reduce code duplication and thus the maintenance cost of our scripting extension that makes use of it. So we have this cool infrastructure. Let's see how it works under the hood. So first, the user needs to import their script into LLDB and register their class, the class that the extension will want to call into. This part varies for each extension, since there is different command and API for each of them. So first you import your script, and this is how we do it for a scripted process. You just run your process, and then you pass the name of your Python module and the Python class that will control your process, basically. Then we need to create the base extension interface as well as the scripting language specific interface. And to do that, we look at LLDB default scripting language to pick which scripting interface to use. So in this case, Python is, by default, Python is our default scripting language in LLDB, so we'll use the Python interface for that. Once the interface are ready, we can instantiate our script object, and we'll need to keep a reference to it. This is used to make the methods call. So every time we want to make a method call, we need to pass that object, basically. So if we read the Python data model documentation, we also see that in Python, classes are callables. So the argument of a call are passed to the init function to initialize a new instance. So that means that when we want to instantiate a new object in Python, it's the same as basically making a function call. And that makes it very convenient because it's helped us simplify our infrastructure even more. So let's say we want to now make a call to read memory at address. What would happen? First, we call the read memory at address a method from the scripted process interface. And this will call the overridden method because it will basically forward, so basically when we call it on the scripted interface, that will dynamically dispatch it to the Python interface. And this method is very trivial because it just forwards all the arguments to the dispatch method, and that's what does all the heavy lifting. Because this is implemented in our Python interface. So it's shared in all the scripting extensions, basically. It's shared by all scripting extensions. So the dispatch method makes use of partial template specialization for the return types and parameter packs for the arguments and other generic programming techniques to be able to take anything as an input and return any specialized type as an output. And yeah, as I mentioned, it's shared and used by all scripting Python interface. So it means that now our code to call script methods from C++ is centralized. So it can help us narrow down any potential point of failure in the future. So first, dispatch will need to resolve the method objects from the script object, the methods from the script object that we've created earlier. And in this part, we do some sanity checks, make sure that the object is well-formed, that the class actually implements the method. And this is also where we checked that the method is marked abstract in the base class implementation. So if the user forgot to implement it in its own implementation, we can trigger an error. Then we're still on the C++ side. So we need to convert the argument that we're going to pass to Python before making the call. So for primitive types such as int, float, and double, or C strings, Python can convert them seamlessly to their Python native equivalent. But luckily for LLDB, we can use the types that are already exposed through the scripting APIs and that are available in our Python bindings. So it works out pretty well. And then we can just rely on Python object calling API that provide various functions with different calling convention to make the method call. So finally, after performing the method call, we need to transform back the return objects from the Python to a C++ type. But we also need to do that for the arguments, because in Python, all the arguments are passed by reference. So like if we had any C++ argument that was a pointer or reference, we'll need to convert it back as well. So this is how it works. And to recap, here we introduce a new base class implementation in our Python module that should help us reduce the amount of required boilerplate code for our user when writing new scripting extensions. We've redesigned the LLDB website to provide a better user experience when searching for documentation. And we're using the documentation in the scripting extension of the base class to keep the website up to date. And we've built a unified, robust, and generic infrastructure to call methods from user scripts, which will help us reduce code duplication and our maintenance costs. But with all of that, there's still many things to do, and we're still investing in making LLDB more approachable by our user and our new user as well. So there's a lot of work to be done still. So recently, I started working on a way to generate scripting extension templates directly from LLDB. So basically, first we would describe like all the available extension, what they do, and what command or API you can use to interact with them. But also, I would like to be able to generate like the base skeleton of a scripting extension so that the user can only have to fill in the blanks. So hopefully that makes it more ergonomic for the user. And finally, I want to make a quick call to action. So there are still many scripting extensions that need to be migrated to this new infrastructure. So if you're familiar with any of the remaining one, feel free to contribute and feel free to add me as a reviewer. I'd love to take a look at your PRs. And thank you for your attention. Do you have any questions?
We have a microphone up front, or I can also come and visit you.
Hey, what's the discoverability story for your APIs? Like, if I say script, right, and start typing, do I get auto-completion, or do I always have to go to the documentation, or was it?
Yeah, so there is some, when you're in the embedded interpreter in LLDB, you have some auto-completion for the method names. So you also have like a help from within the embedded script interpreter that shows you all the methods implemented. And yeah, like we want to make that even more obvious to the user. So that's why I'm working on this like template, like scripting templates command that would also tell you, okay, this is how you instantiate a data, like this is how you use a data formatter, or this is how you use a custom command in LLDB. And even like for the most like the laziest user, like have this like base skeleton, so they just need to type one line basically. So yeah.
So I usually interact with LLDB through the LLDB plugin in VS Code. And I wonder, is there any documentation for people like me who kind of, like, I'm not sure if I'm talking to the debugger or if I'm talking to some VS Code extension. Like, is there any, say, help for us simple people?
So VS Code uses like an interface called DAP, and this is how. So it's different from what I've presented here. Is there anything in particular that you'd like documentation for?
I'm sort of wondering on the documentation side, because I feel like it would be very useful to at least have some sort of help for, like, because I don't know which tree I should be barking up, if that makes sense. Like, I have some sort of need, like for instance, I would like to write an extension that makes, for instance, I don't know if you use variants in C++, but these create an unholy amount of noise. And I would like to fix that. But then I kind of get lost because I don't know, is this something in what I've just learned is called the debug adapter protocol? Is it something I have to do in LLDB? It's also a question who is to document that. I don't know. But you probably know more about it than me.
So are you, like, to take your example, well, like if you use like the variants in C++, you don't have like a good variable view. Is that an issue you're facing?
Also it creates, like, let's say I have a variant with 10 possible inhabitants. Then I would get like a tower of 10 stack frames.
Yeah. So
and also the variable view is also, it'll just give me a byte which represents the number, like the index. So there's many things. Yeah.
So for this specific example, like I guess this is part of the standard library, right? So this is something that I love you to file an issue for that on GitHub, so we can provide, because LLDB provides its own data formatter embed, like for the standard library types. But in the meantime, you could also implement your own data formatter in Python that will hopefully help you solve your issue.
Maybe I can file an issue and fix it.
Yeah, or send us to us. So
Yeah, so the starting point, I think, would be the data formatter section on the LLDB website. But if it's a feature of the C++ standard library, LLDB should also support it out of the box. Yeah, let's mix it up.
Hello. This question might be a little bit out of scope of your work. So recently I was running the CPython interpreter within GDB, and there was very tight integration with PyDebug in that I was able to debug from both a Python perspective and also kind of the system, you know, the register dwarf perspective.
Okay.
But that functionality seems to be lacking from LLDB. Is your work something that would enable replication of that integration? So
yes, yes. When you write like a Python scripting extension, like a Python script for a script extension, you could have a breakpoint command, like a breakpoint a Python breakpoint function call in your scripts, and that would, like when you run it in LLDB, it will stop in the Python debugger in LLDB.
Okay.
So you'll be able to inspect your Python, like the Python state basically from within the LLDB debugger.
Oh, excellent.
Although I should mention that if you're like LLDB has two modes, asynchronous and asynchronous mode. So in the asynchronous mode, you might like the prompt from the Python debugger might flicker with the LLDB prompt. So make sure you're in synchronous mode. So hopefully that doesn't happen.
Thank you very much.
No problem.
Thank you for all the questions. The next talk will start at 11. Maybe you can follow up in further.
Thank you.